Hi, we are Team 31. My name is Dshante Smith. This is Tomika Walkin, and this is Maria Aramayo. We'll be doing the 4-bar mechanism analysis and animation, along with the synthesis of a slider crank mechanism. The agenda for this presentation consists of the introduction of mechanisms and a little background information and history about mechanisms, the 4-bar mechanism analysis and application of it, along with the synthesis of a slider crank and the application of this mechanism type, and a conclusion of the project. What is mechanisms? A mechanism is a kinematic chain in which at least one of the links is connected to a frame of ground where the ground is also considered to be a link. The central theme for mechanisms is that it has a rigid body connected together by different joints. It is a combination of all of these different rigid joints and bodies formed and connected so they will move with definite relative motions with respect to one another. The 4-bar mechanism, it consists of 4 revolute joints, and the Grashoff's theorem is used which is a ratio of the link length, and this is based on the motion characteristics. There are 3 different types of motion. You have double crank, when both of the links are connected to the fixed link, and this can do 1 full rotation. Then you have double rocker, when both of the links connected to the fixed link can only oscillate. Then you have the crank rocker, when one of the links is connected to the fixed link and this oscillates while the other one does its full rotation. Synthesis of mechanism. Synthesis. This refers to an irregular motion by 2 means of 1 degree of freedom mechanisms. It refers to anything except either uniform rotation about a fixed axis or uniform rectilinear translations. It includes cams and linkages. The difference between cams and linkages is that cams can be very expensive. They tend to be unreliable, and they're difficult in terms of the design. The linkages, on the other hand, they're considered to be inexpensive to create, and they're more reliable than the cams. There are 4 possible types of 4-link mechanisms. You have 4-bar linkage. You have a slider crank, which is what we did for this project, for the synthesis. Then you have elliptic trammel, and then you have Rapson slap. A little history of mechanisms. James Watt is considered to be the person who gave birth to mechanisms in terms of starting it up. He created the steam engines, and when they say created, he really wanted to apply thermodynamics to it. So this is where he came into play, because these steam engines already existed in Egypt, but he kind of revamped it, and he saw that you needed to apply thermodynamics, and he wanted to use rotary joints and long links to create more efficient steam engines. He also created the first servo mechanism called the fly ball governor. This made engines much more safer and reliable. Another person, and here's a picture of him with the mechanism he created. Then another person who played a large role in the history of mechanisms is Leonhard Euler. He was the first mathematician to study the mathematics of linkage synthesis. Another person who plays a role in the history of mechanism is Sir Robert Ball. He was the first to implement the screw theory, and what this screw theory was about was a generic study of linkages, motion, and planar and spatial. The first mechanism that was created was the lever. It was very simple in terms of its design. It was basically a lever, which was the link. It had a fulcrum, which was the joint, and the ground, which was a link. We'll now have Maria to talk about the 4-bar mechanism, analysis, and application.
So we'll be talking about the 4-bar mechanism analysis. This is our 4-bar design, and we had to select measurements for our link R1 and R4. And our input angle is going to be the angle that the joint makes with the horizontal. We're using the principle of Grashoff's in order to make this a double crank mechanism, and we'll select it R1 as 15 centimeters and R4 as 50 centimeters. And we're going to be calculating the angles of motion for joint 2 and 4 for closure 1 and 2. Next. We're going to use the loop equations to calculate the full rotation of both closures. And here's an example of closure 1. As you can see, the angles of theta 2 and theta 4, they go all the way from 100 and they end up in 100 again. And for theta 4, it starts at 50 and it goes all the way and it finishes at 50. That means they make a full rotation. In order to calculate the trajectory of the point S in a coupler, we did the equation to calculate the points of XS and YS for every input angle. And this is the graph that we plot in a Y versus X graph. And we see that the coupler makes also a full rotation as the angle starts from 0 to 360 degrees. In order to calculate the angular velocities, we have derived the loop equations, and we calculated the angular velocities for joint 2 and 4, and then we plot a graph to see the respective changes with respect to theta 3, which is our input angle. And then in order to do acceleration analysis, we derive it again, and we see that these graphs are the derivatives of the previous graphs. So that means our results are correct. This is a double crank mechanism that we have designed in SolidWorks. We follow the same measurements, and when we tested it, it made a full rotation as we predicted. And this is the animation that we have created. As you can see, both cranks make a full rotation as the input of angle 3 starts changing. This is a 4-bar mechanism application that we have selected. This is a fair ride called Crazy Bus, and they have used the same principles. As you can see, the distances between the arms could be our link 1. The arms are link 2 and 4, and the bus is link 3. In this concept, the angle of R3 doesn't change, so the input angles could be theta 2 or theta 4, and also the distance here is fixed, therefore link 1 is fixed. Design that we have created in SolidWorks, and we have also created an animation for this. These are other applications that we have selected for a 4-bar. For example, as a double rocker, we have a closing door mechanism, and as a crank rocker, we have a windshield wiper. And as you can see, this is the mechanism with the links and the path that every link follows. And then here we also have the 4-bar. As a conclusion of this, we calculated the position analysis, the velocity analysis, and acceleration analysis. We also did a trajectory analysis for the point of a coupler, and we created the double crank animation in SolidWorks, and we have also selected other real applications of a 4-bar. And this is a concept that we see in everyday life, and it helps us to achieve tasks. Thank you. And now we're gonna follow with Tomika. She'll talk about the slider crank mechanism and applications.
Now we will be discussing the slider crank mechanism synthesis, and this is just a preview of what we constructed in SolidWorks, the different positions that the point C had to travel through, which makes a straight line. So initially what was given were 3 lines, A1, B1, A2, B2, and A3, B3. The center of the circle A0 passes through these 3 points, and we were able to find this pole position using this formula, and our results are here. The radius of this circle is our R2, which is one of our values which we had to solve for. Next, we had to find the pole positions P12, P23, and P13, which was found using these various equations. Here we have the results in X and Y format. Next, the image pole position was found, P'23. We had to use various formulas and we came up with the X and Y positions over on this side. And then we found the origin of this circle of slides, which is P0 X and Y. The radius was called RS. Next, we selected a point on that same circle of slides using points P12, P13, and P'23. We chose a C, X value, and using this formula, we were able to find the 2 corresponding Y values. Then using this set of equations over here, we found the coordinates in the local capital XY coordinate system. Then we were able to obtain values for C2 and C3. And here we found R3, which was our last unknown. Here you can see the diagram depicts how point C1, C2, and C3 formulate the straight line that is needed. And this is just an example of one of the applications we chose, an internal combustion engine. And here is an animation of the mechanism we designed in SolidWorks. As you can see, this is point C moving in a straight line on the slider. This is the point A0, this is point B, point C. I'm sorry, this is point A, B, and C. And in conclusion, the goal was to design a slider crank which passed through 3 initial given points. The major steps included determining the location of A0, calculating coupler points C1, C2, and C3, finding the direction of the sliding coupler, and determining the lengths R2 and R3. Our results were we were able to successfully complete a SolidWorks analysis and assembly of our slider crank. Now we will have the overall conclusion of the project. Each team member contributed a great deal in making this project a success. Each team member was able to pull her own weight, and if anyone's faced any specific problem, we were able to share insights and able to overcome these problems. The teamwork demonstrated in this group was effective and efficient, and the results of this report should prove just that.
We want to thank you for your time and hope you enjoyed our presentation.